Hey everyone, welcome back. This is week 10 of my series where I work through machine learning from the organization perspective. So this is a short week for me, but I wanted to make a video before I leave. So today I wanted to cover something I left out last week, which was composition rules for convex functions. So this is section 3.2.4 in the Boyd book. So last week we covered how to take the pointwise max or supremum of convex functions. Today we're asking a different question, but equally as important. If I compose two functions, how does the convexity carry through? So before diving in, we should talk about why this matters. A huge number of functions in ML are actually compositions of basic functions. Things like the exponent function or like a log of a concave convex function. A lot of these loss functions are built on layering transformations on top of each other. So if you know the rules for when composition preserves convexity, you can look at, a complicated looking function and then immediately recognizing it's still convex and therefore still tractable to optimize. So the setup is this. We have two functions, h and g, and then we define their composition f. So f is defined as the function of h applied to the function of g, which is applied to x. So it's worth pausing on the domain of f. So of course, whatever x is must also be in the domain of g. That's why you see this here. On the other hand, this input of h, the g of x, must also be in the domain of h. So both constraints matter, and we'll see later the shape of the domain of h in particular is going to be important. So the question we're asking is, what conditions on h and g guarantee that f is convex? So to start out, let's start with the simple case, or the scalar case, when h is a function that takes a real number and outputs a real number, and g is the same. And so f takes the input, which is a real number, and also outputs a real number. So this won't be the full general result, but it gives us exactly the right intuition for the rules. We also assume that h and g are twice differentiable, which again is not the full general setup. In this context, f is convex if and only if the Hessian of x, in this case the second derivative of x, because it's one-dimensional, is greater than or equal to 0 for all x. So using the chain rule from calculus, we can calculate the second derivative of f. And then we look at each term and see what needs to be the case for this expression to be greater or equal to 0. So looking at these terms individually, so the first term, we notice that we have this part here, which is always non-negative because it's squared. So the sign on the first term is entirely determined by h double prime g of x. If h is convex, meaning the Hessian is positive, or in this case, since it's one-dimensional, the second derivative is greater than or equal to 0 everywhere, the whole term is non-negative, regardless of what g does. On the other hand, the second term is trickier. The sign depends on the interaction between h prime and g double prime. So this is the slope of h, and this is the curvature of g. For this term to be non-negative, we need these two factors to have the same sign. So this basic analysis gives us 4 different rules for determining if f is convex or concave. Alright, so let's go through the rules for when f is convex, or the second derivative is greater than or equal to 0, or since it's first only one dimension, the second derivative is positive. Okay, obviously, if every term is positive, then this satisfies this condition. So that means that the second derivative of h, so the curvature of h is positive, and it's non-decreasing. So h is, pointed upwards. And we also have G double prime or the curvature of G is positive as well. We also have this possibility where the second term have both negative, and since they multiply, that becomes positive. For f to be concave, that's when the second derivative or the Hessian is negative. So in this case, we can have these two results. We're basically looking for opposite signs on each term. So let's go through an example. In this case, a simple first example where we take the exponent of g of x. So in this case, our h or outer function is the exponent function, right? We take the input g of x and we exponent. And of course, the domain of h is the real numbers as well. So taking derivatives of h, we see that the first derivative, of course, is e of t, which is non-decreasing. It's always greater than 0. And the second derivative is also, again, greater than 0, which is convex. So look here, we have h is non-decreasing and it's convex. So rule 1 applies. And so if g is convex, then f is convex as well. Okay, so the outer function is a log function. We take input g of x and we apply log to it. And the domain of h is positive real numbers, right? It can't be 0, it can't be negative. A log is not defined on that domain, so it must be positive. Okay, taking the first derivative, it's 1 over t, right? Which is always greater than 0 for positive real numbers. The second derivative is always negative for positive real numbers. And so we look at the table, it says, non-decreasing, and, h is concave. So rule 3 applies, and so that means that if g is concave, then f is concave as well. Okay, so hopefully you get the idea, but we have to be careful. In our last example, we sort of hinted at a technicality which actually becomes important. We saw a domain which was actually not defined on all real numbers. And so let's explore that a little bit further. So everything we just talked about, at least the theory, was assumed that g and h are defined in all real numbers. But of course, in general, h might only be defined on some subset. And when that's the case, the non-decreasing or non-increasing condition has to be stated more carefully. The general result requires that the extended value extension of h is monotone, not just h itself is its own domain. So here's the extended value extension of h. When x is in the domain of h, we just have the normal function h here applied, but depending on whether h is convex or concave, we should just apply infinity when x is not in the domain of h. So what does the extended value function non-decreasing actually mean geometrically? So of course what non-decreasing means is that when you have input x is less than equal or less than y, the function evaluated at x is less than equal to the function evaluated at y. That's what it means. But assume when h is convex here. So let's think about the subtle implication of that. Let's pretend that the domain of h is only defined starting at some point a. So the domain of h goes from point a to point, goes all the way to infinity, let's say. So it starts from some point a on the number line, extends all the way to the right. In that case, we can take some x to the left of a, and the extended value function evaluated at x will be infinity. But if we take some y on the right side of a, then that value y must necessarily be less than infinity because it's applied in the domain of h. So this is a contradiction because we assume that h is convex. So what that means is that the domain of h must be extended all the way to the left side, or to negative infinity, when H is convex. So in other words, when you check a composition rule, you're not just checking that H is monotone on its domain, or the second Hessian, or sorry, the Hessian. You're checking that the domain itself has the right shape. So concretely, here's an example that shows why all this technicalities is important. So let's take when g of x is x squared, which of course is convex on R, and h of x equals 0, with the domain of h being, let's say for 1 to 2. H is convex and is non-decreasing. But let's look at what happens to the domain of f. So the domain of f is x must be in the domain of g, but g is domain of g is real numbers, such that x squared is between 1 and 2. But of course that this means that we have this unit here, which is not a convex set. So f cannot possibly be convex. So why did this fail? This failed because the extended value function for, let's say, -1, so for h, tilde of -1, that's positive infinity. But, h tilde of 1, the extended value function is 0. So h is not non-decreasing, even though h is non-decreasing. Okay, so now we have all that under our belt. Let's extend it to the vector case. So here, G maps R of n to R of k, and H maps R of k into R. So F, the composition of H and G, maps R of n to R. So as in the scalar case, we start with the differentiable setting to build some intuition. Now here, without loss of generality, we can actually restrict to n equals 1. This is possible because convexity is determined by behavior along arbitrary lines. So here is the second derivative in the general case. As with before, we need both terms to be positive. So looking at the first term, which is more simple, we see that this is a quadratic form. And so the only way for this term to be positive if the Hessian is positively semi-definite. On the other hand, looking at term 2, we can write it out as follows. So the second term is non-negative when each partial derivative of h and the corresponding gi have the same sign. Okay, so let's look at an example. So let's take the example of h, which maps a k-dimensional vector into a real number by taking the sum of the exponent of its elements and then taking the log. So, of course, the domain of h is the R of k. So let's see what the behavior of f is. So you can verify that the Hessian of h is positively definite, or in other words, h is convex. And we also show here that h is strictly non-decreasing for each argument. So therefore, if each g of I is convex, that means that f is also convex. By the way, this function appears everywhere in machine learning. The softmax is often called cross entropy loss and other things too. Next, we look at the example of LP norms, in particular when p is greater than or equal to 1. So we want to show that the LP norm of G is convex when each G of I is convex and non-negative. To apply the vector rule, we need to define H on all of Rk. So this is for the extended value extension. So the trick we can use is as follows. So all we did was we just defined this tricky little max function, which basically just ensures that H is defined everywhere. And for z greater than or equal to 0, reduces to the usual LP expression. Okay, and then like before, you can show that the Hessian of h is positively definite, or the second derivative is positive for all directions. And here I just shown that h is non-decreasing in each argument. Here in our context, each g of I is convex and non-negative, so that means that the LP norm of this convex function is also convex. So lastly, let's look at the geometric mean. So we take some k-dimensional vector. We find the geometric mean and we ask, what is the convexity of after applying this geometric mean to this vector z? We can show that the geometric mean on Rk, the positive vectors, is concave and non-decreasing in each argument. Note that the strict positivity is required here. The geometric mean is not concave if any zi is allowed to be 0, because the domain of positive vectors is open and the concavity property breaks down at the boundary. Like I mentioned, H is convex, but here I just showed that it is also non-decreasing as well. So to sum it up, since G is concave in each argument and Gi is non-decreasing, or in fact strictly increasing for each argument, that means that the function f is concave. Alright, so that's it for week 10. Traveling next week, but I'll get right back into it once I'm back. So I'll see you then.